On December 13th, 1972, Eugene Cernan stopped his vehicle at the crest of a hill, paused, then opened up the throttle, his tires kicking up a giant rooster tail of dust as he barreled down the slope. By the time he reached the bottom, he had clinched a speed record that still stands to this day, 17.9 kilometers or 11.2 miles per hour. While this might seem like a snail's pace even by 1970s standards, it should be noted that this feat was achieved not on Earth, but rather on the surface of the moon. Cernan was the commander of Apollo 17 and his record-breaking vehicle, the Lunar Roving Vehicle, or LRV. A marvel of mid-century engineering, every bit as impressive as the command and service module that carried the Apollo astronauts to the moon, the lunar module that landed them on its surface, and the massive Saturn V rocket that launched it all into space, the LRV was designed to overcome dozens of daunting challenges, right down to how to fit it in and get it out of the lunar module, as well as how to get it to operate reliably for days in the extremely harsh environment of the lunar surface. Yet, the remarkable moon buggy passed all these tests with flying colors, and on the last 3 Apollo missions, 15, 16, and 17, allowed the astronauts to roam farther and make far more scientific discoveries than would have ever been possible on foot. This is the fascinating story and incredible engineering of the only manned, wheeled vehicle to ever drive on another world. Just before we dive into that, every business owner says they want to scale, but most businesses are still operating quite messily behind the scenes. Leads coming from one platform, emails from another, client notes buried in spreadsheets, automations half working, and every month you keep adding more tools, hoping it somehow fixes the problem. It usually doesn't, because the issue isn't generally effort, it's the system. That's where today's sponsor, High Level, comes in, built to solve exactly that. It's an all-in-one platform where you can manage leads, build funnels, automate follow-ups, track your pipeline, handle bookings, and manage client communications all in one place. Instead of stitching together 6 different subscriptions, High Level gives you one system that actually works together, so you can create automated workflows, build landing pages and funnels, manage your CRM, and keep your entire business organized without constantly switching tabs. Once everything runs inside one platform, it becomes fully clear how much time gets wasted managing disconnected tools. So if you want to try out High Level for yourself, you can start a 30-day free trial using my link below. Run your business from one platform: lead capture, automation, CRM, client management, and more. Long before the Apollo program was officially announced in 1961, engineers and science fiction writers recognized the value of giving future moon explorers some kind of wheeled vehicle to increase their mobility. Most early concepts for such vehicles were large, truck-like contraptions with pressurized cabins, allowing the astronauts to operate in so-called shirt-sleeve conditions, not unlike in the phenomenal film The Martian. Such vehicles appear in Polish science fiction writer Jerzy Żuławski's 1901 novel On a Silvery Globe, and Belgian cartoonist Hergé's 1952 comic book Explorers on the Moon, in which intrepid globe-trotting journalist Tintin becomes the first person to set foot on Earth's satellite. That same year, Wernher von Braun, the former Nazi rocket engineer who developed the V-2 ballistic missile and was brought to the United States after the Second World War as a part of Project Paperclip, wrote a series of articles for Collier's Weekly magazine with the delightfully gung-ho 1950s title of Man Will Conquer Space Soon, in which he speculated on what future space missions might look like. In these articles, he described a hypothetical 6-week expedition to the moon equipped with specially designed 10-ton tractor-trailer vehicles for hauling supplies. These articles were later adapted into 3 episodes of the Disney anthology TV series Disneyland, Man in Space, Man on the Moon, and Mars and Beyond, in which von Braun was prominently featured. Once the Apollo program officially got underway, von Braun, by now the director of the newly formed Marshall Space Flight Center in Huntsville, Alabama, commissioned a series of studies in cooperation with various corporations, including Lockheed, Bendix, Boeing, General Motors, Brown Engineering, Grumman, and Bell Aerospace, to evaluate the feasibility of building a wheeled vehicle for lunar surface exploration. Directed by MSc engineer Severo Moria, these studies came up with a number of theoretical concepts, including the Lunar Logistics System, or LLS, the Lunar Scientific Survey Module, or LSSM, the Mobility Test Article, or MTA, the Lunar Traversing Vehicle, or LTV, and the Mobility Laboratory, or MOLAB, all of which followed the same general form factor of a large, truck-like vehicle with a pressurized cabin and 4 or more large wheels driven by electric motors. At first, the primary challenge in designing such vehicles was the nature of the lunar surface, which in the late 1950s and early 1960s was largely unknown. Some astronomers speculated that millions of years of bombardment by meteorites might have buried the surface under a blanket of dust several feet deep that would instantly swallow up any lander, rover, or astronaut that touched down on it. As a result, early lunar vehicle concepts incorporated a variety of exotic drivetrains, including tank-like caterpillar tracks, giant balloon tires, and even horizontal Archimedean screws to let them float over or plow through this theoretical ocean of dust. However, all of these speculations came to an end once NASA succeeded in sending unmanned probes to study the moon up close. In 1964 and 1965, the Ranger 7, 8, and 9 probes successfully photographed and impacted the lunar surface, while on April 20, 1967, Surveyor 3 soft-landed and used a small, remote-control scoop to trench the surrounding soil. This mission revealed that, contrary to long-held fears, the lunar surface was largely solid with only a thin dusting of dust or regolith. This was a huge relief to lunar rover designers as it meant their vehicles could make use of more conventional and well-proven propulsion systems. Unfortunately, by this time the MOLAB concept had run into another, more fatal roadblock. As covered in our previous video, How NASA Learned to Land on the Moon, NASA planners initially selected what was known as a direct ascent mission profile for Apollo. This scheme utilized a single integrated spacecraft that would carry the astronauts to the moon, land on the surface, lift off, return to Earth, and re-enter the atmosphere. While theoretically straightforward, in practice, this strategy suffered from a host of practical drawbacks, chief among them being that it was extremely heavy. The command module needed to be robust enough to survive the heat and stress of atmospheric re-entry, while the service module needed to carry all the equipment and consumables needed for the entire mission to the moon and back. All this mass needed to be safely soft-landed on the moon and blasted off again, requiring the use of a massive rocket engine and large quantities of fuel, so large in fact that despite the moon's gravity being 1/6 that of Earth, early estimates put the total required mass of the spacecraft at a whopping 90 metric tons. Such a gargantuan spacecraft would, in turn, require an equally gargantuan rocket to haul it from Earth to the moon and back. Known as the Nova, this behemoth would have stood nearly 110 meters or 360 feet tall, weighed 4.5 million kilograms or 9.9 million pounds, and had a first stage delivering a total thrust of 61,925 kilonewtons or 13.9 million pounds of force. By comparison, the Saturn V rocket that ultimately took humans to the moon stood 86 meters or 282 feet tall, weighed a mere 2.8 million kilograms or 6.2 million pounds, and had a first stage thrust of 34,500 kilonewtons or 7.75 million pounds force. Not only were engineers unsure if the Nova could even be constructed by the end of the decade, but the rocket would have been too powerful to launch from the pads at Cape Canaveral, and indeed, one proposal called for the rocket to be launched from hollowed-out cliffs in Hawaii, while another called for Nova to be fitted with nuclear rocket engines, which would have required launching it from an uninhabited island or giant barge to prevent contaminating populated areas with radioactive fallout. Direct ascent would also have left no room aboard the Nova for vehicles, habitats, or any other equipment needed for long-term exploration or colonization of the moon. It was thus planned to launch a second rocket carrying an unmanned lunar surface module, or LSMT, truck to land such equipment alongside the astronauts. This dual launch assumption allowed for the use of large, pressurized cabin vehicles like the MOLAB. But by 1962, in part thanks to the efforts of an extremely dedicated NASA engineer named John C. Hubble, NASA had switched to a far more efficient mission profile known as Lunar Orbit Rendezvous. In this scheme, the actual lunar landing would be carried out using a separate, dedicated craft known as the Lunar Excursion Model, or LEM. Upon entering lunar orbit, 2 of the 3 Apollo astronauts, the commander and lunar module pilot, would transfer from the Command Service Module, or CSM, to the LEM via a docking tunnel, leaving the 3rd astronaut, the Command Module pilot, or CMP, behind. They would then ride the LEM down to a landing on the lunar surface. Once their mission was complete, the astronauts would blast off from the lunar surface and rendezvous and dock with the CSM in lunar orbit, whereupon the LEM would be jettisoned and the CSM would carry the astronauts back to Earth. As the LEM only had to operate in space and did not have to withstand the rigors of atmospheric launch and re-entry, it could be made far lighter than the original direct ascent LSM, and indeed, the final design produced by Grumman Aircraft was a fragile, spindly-looking contraption with skin panels no thicker than a few sheets of aluminum foil and which weighed in at only 5,000 kilograms or 11,000 pounds. This, in turn, allowed allowed the Apollo to use Von Braun's Saturn V launch vehicle, which was lighter, simpler, and faster to develop than Nova. But while Lunar Orbit Rendezvous solved many major problems and ultimately made US President John F. Kennedy's 1961 goal of landing men on the moon by the end of the decade a practical possibility, it also killed all existing plans for a lunar truck-like MOLAB stone dead. There simply was not enough payload capacity aboard the Grumman LEM to carry such a massive vehicle. Nonetheless, recognizing the utility of some sort of lunar mobility aid, NASA continued to study an alternative vehicle light and compact enough to be carried aboard the LEM, including, amusingly, a small electric motorcycle. A more exotic concept proposed by Bell Aircraft in 1965 was the Lunar Flyer, effectively a stripped-down miniature lunar module comprising a platform with a seat, landing legs, and a small liquid-fueled vertical rocket engine that could theoretically carry a single astronaut and 170 kilograms of lunar rock samples over a range of up to 8 kilometers. When this concept was rejected, Bell retooled the design into the Lunar Escape System, or LESS, a space life raft for use in case the LEM was rendered inoperative. As designed, the vehicle could be deployed and assembled by a single astronaut in around an hour and was fueled by propellant siphoned from the LEM's own tanks. Weight and volume restrictions prevented the inclusion of a guidance computer, meaning the LESS would have to be flown manually. Using nothing but a simple 8-ball attitude indicator, a clock, and visual references such as the lunar horizon, the pilot would have to execute a series of timed attitude corrections during the ascent in order to place the LESS in roughly the same orbit as the command service module. Meanwhile, the command module pilot would use a radio and light beacon on the LESS to guide the CSM to a rendezvous. Once the LESS was secured to the CSM's docking probe, the command module pilot would don his spacesuit, depressurize the command module, and open the hatch. A successful rescue would require a combination of extraordinary piloting skills and a great deal of luck, especially as the astronauts would have only a few hours until their PLSS life support backpacks ran out of oxygen. But like all other escape pod concepts, LESS was ultimately rejected as too heavy, expensive, and risky. Other lunar mobility concepts were even wackier, such as the Lunar Leaper, proposed in 1967 by Dr. Howard S. Seifert of Stanford University. Effectively a high-tech lunar pogo stick, the Lunar Leaper features a seat or spherical pressurized cabin with an extendable gas-powered piston capable of propelling it and the astronaut inside across the lunar surface in giant 15-meter or 50-foot jumps. Unsurprisingly, this absurd concept was never seriously considered, nor any other lunar mobility proposals. As a result, the first Apollo astronauts were forced to explore the lunar surface entirely on foot. Nonetheless, work on the problem quietly carried on in the background. At the General Motors Defense Research Laboratories in Santa Barbara, California, a team of research engineers, including Sam Romano, his parents mashed their hand against the keyboard Becker, and Ferenc Pavlinks was tasked by NASA's Jet Propulsion Laboratory, or JPL, to develop a small, unmanned wheeled rover for deployment from future Surveyor lunar probes. As part of this project, Pavlinks developed an innovative type of vehicle tire specifically for use on the moon. Traditional inflated rubber tires were unsuited to this application. Not only would a flat be nearly impossible for the astronauts to repair, but few existing elastomers could withstand the harsh, unfiltered UV light and the dramatic temperature swings of plus to minus 120 degrees Celsius or 250 degrees Fahrenheit between sun and the shade without breaking down. All that said, during the 1971 Apollo 14 mission, astronauts Alan Shepard and Edgar Mitchell pulled their tools around using a two-wheeled cart officially known as the Modular Equipment Transporter, or MET, but nicknamed the Lunar Rickshaw. The MET used a pair of nitrogen-filled synthetic rubber tires specifically designed by the Goodyear Tire and Rubber Company, and while these performed well enough, the wheels of a manned or unmanned rover would be subjected to significantly more wear and tear, and thus needed to be far more resilient. And while these performed well enough, the wheels of a manned or unmanned rover would be subjected to significantly more wear and tear, and the results vastly more catastrophic if the astronauts got stranded, and thus needed to be far more resilient. To this end, Pavlinks created a tire made from wire mesh bent into a donut shape, fixed to a central metal hub, and covered in a herringbone pattern of metal strips for traction. Not only did this design replicate the elasticity and shock absorption qualities of a rubber tire, but the flexing of the mesh caused it to automatically shed any soil and rocks it picked up, making the wheel self-cleaning. That's right, Ferenc Pavlinks literally reinvented the wheel. Is there anything engineers can't do? In 1967, Romano and Pavliks went to NASA to pitch their proposal for a manned lunar rover using the innovative wire mesh wheel. Much to their surprise, NASA then informed them that there was space aboard the LEM for just such a vehicle, but precious little. Specifically, a tiny wedge-shaped compartment in Quadrant 1 of the descent stage measuring only 1.5 meters or 5 feet wide, tall, and deep. So for reference, that's around 1 cubic meter or 35 cubic feet. GM could come up with a lightweight and reliable enough vehicle that could fold up to fit into that tiny space. The administrator said NASA would be interested in adopting it for Apollo. Pavliks excitedly rushed home and in only a month constructed a 1/6 scale remote-controlled model of a folding rover, with his wife sewing the cloth components and his son lending a space-suited G.I. Joe action figure to simulate the astronaut driver. Aside from the mesh tires, the most innovative aspect of Pavliks' design was its folding mechanism. The flat chassis was divided into 3 hinged panels, with the end panels folding over 180 degrees to lie flat against the center panel. The wheels then folded inwards on their suspension arms to lie at an upward angle, creating a wedge-shaped package that fit perfectly into the spare equipment bay on the LEM. After taking several home movies of his model around his yard, Pavliks took it to Marshall Space Flight Center and cheekily drove it into the office of director Von Braun, who at that moment was speaking on the phone. Seeing the curious vehicle roll up to his desk, Von Braun reportedly slammed down the receiver and exclaimed, "What have we here?" Then, after Pavliks showed him the films of the model rover driving around his yard, Von Braun excitedly proclaimed, "We must do this." And so it was that on July the 11th, 1969, just 5 days before the launch of Apollo 11, NASA issued an official request for proposals for a Lunar Rover Vehicle, or LRV. Being a government agency, NASA insisted on an open tender process, meaning GM found itself in direct competition with proposals from Boeing, Bendix, Grumman, and Chrysler. Grumman's proposal in particular was an early frontrunner, featuring an innovative conical wheel design that naturally shed rocks and dust. But on October the 28th, 1969, NASA officially selected the GM design, with Boeing Aircraft of Seattle selected as prime contractor and GM as a subcontractor supplying the wheel, drive, and suspension mechanism. The initial cost plus incentive contract of $19 million called for delivery of the first vehicle by April 1971, just 17 months away. By this time, the need for a lunar roving vehicle had become increasingly urgent as severe budget cuts forced NASA to compress its mission schedule. The first lunar lander mission, Apollo 11, was a G-type mission, with the astronauts spending only a day on the lunar surface and performing a single 2.5-hour extravehicular activity, or moonwalk. The next 3 missions, Apollo 12, 13, and 14, were H missions, requiring the astronauts to make precision landings, spend 2 days on the surface, and perform 2 long EVAs. Though, of course, Apollo 13 suffered an explosion en route to the moon and never made it to the surface. And to learn more about the real-life story of NASA's successful failure, please do check out our couple-hour documentary, Hollywood vs. Reality: What Actually Happened During Apollo 13. Apollo 15 was originally supposed to be another H mission, but when, on January 4th, 1970, NASA announced the cancellation of Apollo 20 in favor of the Skylab space station program, it was changed to a longer duration J mission. 9 months later, NASA announced the further cancellation of Apollo 18 and 19, meaning the program would end with Apollo 17, scheduled for late 1972. With the goal of landing a man on the moon by the end of the decade having already been achieved, these latter missions were largely sold on their scientific value. A lunar roving vehicle, it was argued, would allow the astronauts to cover far more ground and potentially make more discoveries in a shorter time and help conserve energy during long EVAs. But while Pavliks and the rest of the GM team had laid much of the groundwork, the Boeing team, under project manager Eugene Cowart, still faced a daunting task. In order to meet NASA's extremely tight deadline, Boeing employees worked up to 12 hours a day, 6 to 7 days a week, for nearly a year and a half straight. One of the greatest challenges was keeping the vehicle's weight down, as every additional pound of weight would require the lunar module to hover for an additional about 1/10 of a second during descent, greatly increasing the mass of propellant required. Every effort was thus made to make the vehicle as sleek and efficient as possible. According to Cowart, by the end of the project, engineers were down to counting tenths of ounces, shaving every sliver of excess metal off the frame in order to stay under the weight limit. In addition to being lightweight and easy for the astronauts to deploy from the lunar module, the LRV also had to be reliable, stable, and capable of negotiating rough lunar terrain, including slopes of upwards of 45 degrees without getting bogged down or slipping over. Towards this end, Boeing built a variety of engineering models, including a static model to assist with human factors, such as the design of the seats and controls, an engineering model to help integrate various subsystems, mass and vibration models to test the vehicle's integration into the lunar module, the operation of its deployment mechanism, and its ability to withstand the stresses of launch, and a so-called 1G trainer to familiarize the astronauts with the vehicle's operation. As the name implies, this vehicle was made significantly more robust than the actual flight article to allow it to be driven in full Earth gravity, and was typically driven over a patch of simulated lunar terrain, aka the rock pile at Kennedy Space Center. However, in order to give the astronauts an idea of how the LRV would handle in 1/6 lunar gravity, the 1G trainer was also suspended from a special weight and pulley system constructed at the Manned Space Flight Center in Houston. Finally, some developmental models were also tested aboard a modified Boeing KC-135 reduced gravity aircraft, aka the Vomit Comet, in the process flying parabolic arcs. The finalized LRV or moon buggy measured 3 meters or 10 feet long with a wheelbase of 2.3 meters or 7.5 feet and a ground clearance of 36 centimeters or 14 inches. Fully loaded, it weighed 210 kilograms or 460 pounds, equivalent to only 35 kilograms or 77 pounds in 1/6 lunar gravity. Despite how trimmed down it was, it could carry upwards of 500 kilograms or 1,100 pounds of payload, including 2 astronauts, tools, scientific instruments, and geological samples, more than twice its own curb weight. Made of welded aluminum alloy tubing, the 3-part folding chassis featured 2 folding tubular metal and nylon webbing seats and Velcro seatbelts mounted side by side with an armrest mounted between them. A trainable color television camera was mounted up front, along with a small, low-gain and folding mesh high-gain antenna for sending and receiving voice, television, and telemetry data to and from Earth, while the rear held a foldable rack for geological sample collection, tools, and other equipment. The 4 wheels comprised 81 centimeters or 32-inch diameter and 23 centimeter or 9-inch wide versions of Pavlik's Resilient tire, made of woven zinc-covered steel mesh covered in titanium traction chevrons mounted to a spun aluminum alloy hub. Each wheel was driven independently by a Declo 190 watt or 0.25 horsepower brushed DC electric motor via a so-called harmonic or strain wave gear drive. This drive transferred torque via an elliptical rotor and a flexible tooth spline. This provided high gear reduction ratios in a compact package and allowed the motors to be hermetically sealed in the hubs and pressurized with nitrogen to prevent dust ingress. And in the event a motor failed, it could be disconnected from its wheel by pulling a pin, allowing the wheel to spin freely. These motors, in turn, were powered by a pair of Eagle Pitcher Industries 36-volt silver zinc potassium hydroxide non-rechargeable batteries with a total capacity of 242 amp hours. This gave the LRV a range of around 92 kilometers or 57 miles. Each wheel was fitted with a mechanical disc brake and mounted on a double wishbone and torsion bar suspension assembly which, as previously mentioned, folded inward to allow the LRV to be packed into the LEM equipment bay. Each wheel was also fitted with a fiberglass fender to prevent it from kicking up dust while driving, and fully loaded, the LRV was designed to achieve a top speed of 9.7 kilometers or 6 miles per hour. Steering was via electric servo motors, and for redundancy, both the front and rear wheels could be steered independently or either disabled as the astronaut chose. Using both steering mechanisms at once gave the LRV a 0 turning radius, meaning it could turn in a perfect circle around itself. Steering was controlled by a T-shaped joystick mounted between the 2 seats. Tilting the joystick forward activated and varied the speed of the motors. Tilting it side by side turned the vehicle left and right, and tilting it backwards activated the brakes. And finally, engaging a switch while pulling the stick backwards put the vehicle into reverse. On all 3 Apollo missions, which used the LRV, the commander always drove while the lunar module pilot assisted with navigation. Next up, mounted ahead and between the seats and control stick was an instrument panel which displayed a variety of data, including speed, pitch, roll, battery charge, and temperature, distance traveled, and heading. To ensure the instruments could be seen even if the astronauts passed into the shadow of a hill or crater, the dials were coated with luminous radioactive promethium paint. Reliable navigation had been a top concern since the start of the LRV program, since on previous missions, astronauts had found it difficult to navigate on the bleak, often featureless lunar surface and easily became disoriented if they wandered out of sight of the lunar module. Worse still, the moon does not have its own magnetic field, meaning a regular magnetic compass cannot be used as on Earth. Instead, the LRV was fitted with a small guidance computer connected to a 2-axis gyroscope and odometer, which continuously calculated and displayed the LRV's distance and heading from the LEM. To calibrate this system, the astronauts used a small flip flip-up sun shadow device similar to a sundial, which relied on the fact that on the moon, the sun moves very slowly across the sky. And indeed, the lunar day, that is, the time it takes for the moon to complete one rotation around its axis, is equal to 29.53 Earth days, or around 1 month. Nonetheless, Apollo astronauts were instructed to never lose sight of the LEM unless absolutely necessary, and to never drive farther away than they could walk back without their spacesuit life support systems running out of oxygen, the so-called walk-back limit. Standard procedure was also for the astronauts to drive out to the farthest planned stop or station and slowly make their way back to the LEM. Initially, the LRV was designed to be entirely spring-loaded, so it would automatically deploy itself from the LEM equipment bay when the astronauts pulled a lanyard. However, Boeing engineers could never get the system to work properly, and the final design was instead manually lowered out of the bay and unfolded using a system of extendable booms, pulleys, and cloth tapes. Some components, however, were still designed to fold out and lock themselves into place automatically, saving the astronauts considerable effort. A similar system was used to deploy the Apollo Lunar Surface Experiment packages, or ALSEPs, which the astronauts left behind on the moon. In addition to weight, another major design challenge which plagued the LRV project was that of disposing of the massive amounts of waste heat generated by its batteries, motor drive, navigation, and other electronic systems. Once all the other essential systems had been designed and optimized, the Boeing team found themselves with a mere 3 kilograms or 10 pounds remaining in their mass budget, meaning that conventional and heavy liquid cooling and radiator systems could not be used. In the end, engineers came up with a brilliantly elegant solution. Heat from the electronics was absorbed by tanks of paraffin wax, which in transitioning from solid to liquid phase kept these systems at a constant temperature of 45 degrees Fahrenheit or 7 degrees Celsius. The wax tanks were then covered with hinged lids to keep out dust while driving, and once the astronauts returned to the LEM after completing an EVA, they opened these lids to reveal fused silica radiator surfaces inside that, during the astronauts' rest periods, radiated the heat from the wax out into space. Once battery temperatures dropped below a certain level, a bimetallic strop device automatically released a hold-open catch and closed the lids. The last major engineering challenge was to adapt the A7L spacesuits worn by the astronauts to be compatible with the LRV. The suits worn by crews of Apollo 7 through 14 were not designed for sitting and had limited flexibility in the torso. For the J missions, suit manufacturer International Latex Corporation, makers of Playtex brand feminine support garments, added flexible joints at the waist and neck to allow the astronauts to sit comfortably in the rover and provide greater all-around visibility while driving. The entry zipper, which originally ran down the back of the suit, now ran diagonally across the chest, with the oxygen and water connectors for the portable life support systems, or PLSS backpack, being rearranged from 2 vertical rows down the chest to 2 triangular clusters on either side of the zipper. Given the longer duration of the J mission EVAs, the PLSS was also modified to carry more oxygen, cooling water, and carbon dioxide scrubber canisters. Boeing delivered the first LRV to NASA on March 10, 1971, just 2 days ahead of the contracted deadline. However, cost overruns had caused the total price tag to double from the original $19 million to $38 million, much to the consternation of budget-conscious NASA administrators. In total, Boeing produced 4 production articles, the last of which was never flown following the cancellation of Apollo 18, and instead used for spare parts. The first mission to use the LRV was Apollo 15, which launched from Kennedy Space Center Launch Complex 39A at 1334 Universal Coordinated Time, or UTC, on July 26, 1971. Crewed by Commander David Scott, Lunar Module Pilot James Irwin, and Commander Module Pilot Alfred Worden, the Command Service Module, or CSM, Endeavour entered lunar orbit on July 29th, whereupon Scott and Irwin transferred to the Lunar Module Falcon and began their descent toward the lunar surface, touching down on the evening of the 30th. Over the next 3 days, the 2 astronauts made a total of 4 EVAs, totaling 19 hours and 7 minutes, during which they successfully deployed the LRV and became the first humans to drive a wheeled vehicle on another world. Right away, however, they encountered a troubling problem. The front steering mechanism refused to work. Thankfully, however, this contingency had been planned for, and otherwise the LRV performed exactly as designed, much to Boeing and NASA's delight. Indeed, in anticipation of this historic event, Boeing had fitted the LRV with a plaque bearing the inscription, "Man's First Wheels on the Moon, delivered by Falcon, July 30th, 1971. Irwin and Scott drove a total distance of 27.9 kilometers, or 17.3 miles, collecting 77 kilograms, or 170 pounds of geological samples, including the so-called Genesis rock, a 270-gram piece of anorthosite discovered near Spur Crater, originally thought to be part of the moon's primordial crust. Later analysis, however, revealed it to be between 4.5 billion years old, younger than the moon's formation, and that another sample collected during the previous Apollo 14 mission was slightly older. In addition to sample collection and other scientific activities such as deploying the mission's ALSEP instrument packages, Scott and Irwin also laid out a memorial called Fallen Astronaut, consisting of a small aluminum sculpture of a spacesuited astronaut designed by Belgian artist Paul van Hooijdonk, and a plaque bearing the names of 14 American astronauts and Soviet cosmonauts who had died on missions or in training up until that time. But perhaps the most memorable event of the mission took place during the fourth and final EVA, when Commander Scott performed a simple demonstration of Renaissance Italian scientist Galileo Galilei's assertion that in the absence of air resistance, all objects fall at the same rate regardless of mass or shape. Standing in front of the LRV's television camera, Scott dropped a geological hammer and a falcon feather, a tribute to the mission's lunar module, which, as expected, hit the ground at the same time. Meanwhile, orbiting overhead in Endeavour, CMP Al Worden conducted extensive surveys of the lunar surface and environment using high-resolution cameras and instruments mounted in the Service Module's Scientific Instrument Module, or SIM bay. Having spent 66 hours and 55 minutes on the lunar surface, on the afternoon of August 2nd, Scott and Irwin blasted off from the moon in Falcon's ascent stage. Prior to entering the LEM, the astronauts had parked the LRV so Ed Fendel at Mission Control could use its television camera to record their liftoff. This required some deft timing, since the nearly 3-second round-trip communications delay between the Earth and the moon meant that Fendel had to send the command to pan the camera upwards before Scott fired the ascent engine. In the event, he failed to keep the stage in frame. After docking with and transferring back to Endeavour, Scott and Irwin jettisoned Falcon's ascent stage, which, as planned, fell back and impacted the lunar surface, generating seismic waves to be recorded by instruments left by Apollo 15, 14, and 12. The reunited crew then spent the next 4 days conducting various scientific experiments in lunar orbit, including deploying a small Particles and Fields Subsatellite, or PFS-1, before burning the CSM main engine and heading back to Earth. And during the return journey, Al Worden performed a 39-minute EVA to retrieve film canisters from the SIM bay's cameras, the first time this had ever been done in deep space. Endeavour separated from its service module and re-entered the Earth's atmosphere on August 7th, splashing down in the Pacific Ocean at 20:45 UTC. During the descent, the mission suffered its only major mishap when one of the capsule's 3 parachutes failed to deploy. However, the remaining 2 were more than enough to slow the spacecraft, and the crew were safely recovered by the aircraft carrier USS Okinawa. Unfortunately, Apollo's many successes were soon overshadowed when it was revealed that the crew had carried unauthorized postal covers to the moon on behalf of a West German stamp dealer. The ensuing scandal saw Scott, Irwin, and Worden reprimanded and removed from NASA flight rotation. They never flew in space again. The next J mission was Apollo 16, crewed by Commander John Young, Lunar Module pilot Charles Duke, and Lunar Module pilot Ken Mattingly, who, as many of you may recall, was pulled from the Apollo 13 due to possibly having contracted German measles and replaced on that ill-fated mission by Jack Swigert. The 3 blasted off from Launch Complex 39A at 17:54 UTC on April 16, 1972, arriving in lunar orbit 3 days later. On the 5th day, Young and Duke transferred from the CSM Casper to the LEM Orion, undocked, and began their pre-descent checkout. Unfortunately, Young soon discovered troubling oscillations in Orion's descent stage backup gimbal system, which normally would have prompted Mission Control to abort the landing and bring the astronauts back home. But after nearly 6 hours of discussion, it was decided that these problems could be worked around, and the go-ahead was given to proceed with the landing, with Young and Duke touching down on the morning of April the 21st. However, due to the landing delay and the possibility of further serious technical mishaps, Mission Control decided to shorten the mission by a full day and trim the third scheduled EVA from 7 hours to 5. Nonetheless, over the next 3 days, Young and Duke performed 3 EVAs totaling 20 hours and 14 minutes in duration and drove their LRV a total distance of 26.7 kilometers. Overall, the mission profile was very similar to that of Apollo 15 and went about as smoothly, though during the second EVA, Commander Young accidentally bumped into one of the LRV's rear wheels, breaking off its fiberglass fender extension. This caused lunar dust to be thrown up and cover the astronauts and the rover, causing battery temperatures and power consumption to rise dramatically. While Young and Duke attempted no repairs, the LRV continued to operate perfectly for the duration of the mission. After spending 71 hours on the lunar surface, Young and Duke blasted off in the early morning hours of April the 24th and reunited with Mattingly aboard Casper. As per Mission Control's prior decision, the crew spent only 1 more day in lunar orbit before deploying the PFS-2 subsatellite and returning to Earth. However, Out of an abundance of caution, Mission Control chose to cancel the planned burn to place the satellite in a higher, more stable orbit, meaning it lasted only a month before crashing into the lunar surface. Like Al Worden on Apollo 15, on the return flight, CMP Ken Mattingly performed a deep space EVA to recover film canisters from the CSM sim bay. Casper successfully re-entered the Earth's atmosphere and splashed down in the Pacific Ocean on the evening of April 27, 1972, the crew being recovered by the aircraft carrier USS Ticonderoga. The third and final J mission, and the last ever of the Apollo program, was Apollo 17, crewed by Commander Eugene Cernan, Lunar Module pilot Harrison Jack Schmitt, and Command Module pilot Ronald Evans. Uniquely among the Apollo astronauts, who were nearly all military test pilots, Schmitt was a civilian geologist, one of 5 scientist astronauts selected by NASA in 1965. Due to the timing needed to reach the planned landing site, Apollo 17 was the only Apollo mission to launch at night, with the Saturn V blasting off from Launch Complex 39A at 5:33 UTC on December 7, 1972. Also along for the ride were 5 additional crew members, 4 male and 1 female pocket mice nicknamed Fee, Fi, Fo, Fum, and Fooey, carried in a special compartment as a part of a biological experiment on the effects of cosmic rays on biological organisms. A similar experiment, called the BioStack experiment, also carried various microorganisms, seeds, and the eggs of animals like brine shrimp and beetles. Significantly, on the way to the moon, Harrison Schmitt snapped a now iconic picture of the full Earth showing all of Africa up to the Mediterranean. Cropped, rotated, and color-corrected, the image commonly known as the Blue Marble remains one of the most reproduced photographs of all time. On December 11th, Cernan and Schmitt transferred from the CSM America to the LEM Challenger and began their descent to the lunar surface, touching down at 1954 UTC. Over the next 3 days, Cernan and Schmitt spent a record-breaking 75 hours on the lunar surface and 22 hours and 3 minutes on 3 extended EVAs. This being the last mission of the Apollo program, the pair had to pack an enormous amount of science and exploration into their stay, a task made much easier thanks to the remarkable LRV. Over the course of the mission, the astronauts drove their moon buggy a total distance of 35.7 kilometers or 22.2 miles and as far as 7.6 kilometers or 4.7 miles from the lunar module. While this was technically beyond the aforementioned walk-back limit, by this time the LRV had proven so reliable that these rules had been relaxed. The LRV also set another record when, on December the 13th, Cernan drove it down a hill, reaching a maximum speed of 17.9 kilometers or 11.2 miles per hour. This remains the fastest speed ever achieved by a wheeled vehicle on another celestial body. In addition to helping transport the astronauts, their tools, and the components of the ALSAP instrument package around the lunar surface, Apollo 17's LRV also carried its own pair of instruments, the Traverse Gravimeter Experiment, or TGE, and the Surface Electrical Properties, or SEP experiment, which the astronauts used to take measurements of the lunar environment at each assigned stop or station. But while overall the LRV worked exactly as designed, as on Apollo 16, the vehicle suffered a mishap during deployment when Cernan accidentally caught his geological hammer under the right rear fender extension and broke it off. Thinking quickly, Cernan and Schmitt improvised a repair using a paper map held in place by a piece of duct tape, but while it is usually true that duct tape can fix anything, unfortunately the omnipresent lunar dust prevented the adhesive from sticking properly, and the MacGyvered fender fell off after 1 hour of driving, coating the astronauts in dust. On the second EVA, Cernan and Schmitt secured the fender with a pair of clamps from a movable overhead light in the LEM cabin, and in this configuration the repair held for the rest of the mission. The fender was later brought back to Earth and is now on display at the National Air and Space Museum in Washington, D.C. Apollo 17 finally came to an end on the afternoon of December the 14th, 1972, when, at the end of their third EVA, Cernan and Schmitt climbed back aboard the Challenger for the last time. Bookending Neil Armstrong's immortal words from 3 years before, Cernan declared,
"This is Gene, and I'm on the surface. And as I take man's last step from the surface, back home, for some time to come, but we believe not too long into the future, I'd like to just let what I believe history will record, that America's challenge of today has forged man's destiny of tomorrow. And as we leave the moon and Taurus literal, we leave as we came, and God willing, as we shall return, with peace and hope for all mankind."
On December 19th, American re-entered the Earth's atmosphere and splashed down in the Pacific Ocean, Cernan, Schmidt, and Evans being safely recovered by the aircraft carrier USS Ticonderoga. As of this recording, it was the last time in history human beings set foot on another celestial body, and until the Artemis II mission of April 2026, the last time they had left low Earth orbit. Much of this final mission success was due to the remarkably capable Lunar Rover Vehicle, and indeed, during Apollo 11, Neil Armstrong and Buzz Aldrin traveled only around 250 meters, or 820 feet, while collectively they and the crews of Apollo 12 and 14 explored an area equivalent to only 2 football fields. Thanks to the LRV, however, the crews of Apollo 15, 16, and 17 were able to explore an area equivalent to the island of Manhattan. As Harrison Schmitt later reflected, the lunar rover proved to be the reliable, safe, and flexible lunar exploration vehicle we expected it to be. Without it, the major scientific discoveries of Apollo 15, 16, and 17 would not have been possible, and our current understanding of lunar evolution would not have been possible. Several other roving vehicles have also visited the moon, though all of them have been unmanned. But whatever form future lunar exploration and colonization missions take, powered wheeled vehicles will no doubt be as vital to their success as they were in Apollo's. Until then, however, while us earthbound gearheads can buy supercars like the Bugatti or the Koenigsegg Jesko Absolute capable of reaching speeds exceeding 500 kilometers or 300 miles per hour, none of us will ever be as cool as David Scott, Bill Irwin, John Young, Bill Duke, Gene Cernan, or Harrison Schmitt, the only men in history to burn rubber, so to speak, on another world.